Good morning, everyone. This is my English speaking practice, and I solve problems on LeetCode. Today, I'm gonna work on unique binary search trees 2. Given an integer array, integer n, return all the structurally unique binary search trees, which has exactly n nodes of unique values from 1 to n. Return the answer in any order. Okay. Makes sense. So, when the input is 3, we should use 1, 2, 3. Yeah, so yeah, we should return all possible unique binary trees. And yeah, the answer is like this: 1, 2, 3, 4, 5, 5 patterns. That's because I don't know. I cannot explain why this is why there are 5 answers, but basically we should check the all combinations. So first, as a root node, we choose 1, and for next, we can choose 2. Yeah. And next, we choose 3. Yeah. But in this case, how about how about 1, 2, and 1, 3? So like yeah, it's within depth 2. It's like triangle. Yeah, because the problem asks us to return all the structurally unique BST. So this structure, I think this structure is same as this structure, because the node 1 have children. Yeah, 2 children, 2 and 3. So so we have to check the structure and check if it's the same or not. Okay. Let's work on import types, generate trees. Yeah. This is difficult for me. I have no idea how do I check the structure? 1, 2, 3 and 1, 2, 3. They are not same. Okay, so I might misunderstand. The depth is one, two, three, and 3, 2, 1 is not the same. Okay. How about 1? How about the node 1 have 2 and 3 as a children? Okay, so the value is not matter in this problem, right? So it's just structure. So root node has right children and right children have left right child. Root node have right child and the right child have a left child. This is one pattern, and root node have right child and right child have right child. Yeah. So the value of node doesn't matter. We don't care about it. We just focus on the shape, structure. So the pattern is, yeah, there are 5 patterns when I use 3 nodes. Okay. That's my understanding. So I will go with this understanding. So we don't care about the value of nodes. So just yeah. So there must be root node and then we have 3 patterns. Just have right node, just have left node, and have both of nodes. Okay. So yeah, the backtracking is suited to this problem. Cause there are three branches. Yeah, and base case is the remaining node. It takes remaining number. Yeah, if it equals 0, yeah, the generation is completed, so we want to append it to the answer, so we declare the array to store the all results, and the function also wait, how to the return type is like this. So we should return the root node for each answer. So that means how to do that? How do I do that? That means okay, skip it right now. The branch one, the current, okay, so it append the child to the left. So yeah, initialize the tree node and update the remaining, and the value would be is remaining, and the left and the right are none at the time. Yeah, so we could append the left node. So we call the backtracking function recursively. Right? Right. So this is like a DFS. So we can find this pattern at first. and then it backtracked and it point here, and at this point the remaining would be 1. So after wait, I see. Append left and try to append right. Yeah, because remaining might be 0. So in this case, we cannot append the additional right node. So at this point, we don't backtrack at this point. We try to append right node. Yeah, if there is remaining, yeah, we can what happened? I'm confused. This function returned. That means the remaining is 0, or yeah. No. At this point, the remaining is 0, and what? Oh? Consume remaining and append the left node. Consume remaining and append the left node. And if the remaining is 0, we finish it and return. How to search this pattern? うんうんうん backtrack and go go to right side is yeah easy. Yeah, it's simple, it's simple work. um, but in this case, look at here and append left, and then yeah, they are still remaining, but it go back to this node, and there is still remaining, so we can go to the right node. Oh, that's so yeah, so we have to branch at this point, go to left when they are still remaining, go to left, or go back. Go left, go back, or go right. Okay, and append the list. Okay. Okay, so we have to backtrack here. That means restore the remaining, and the node left is backtracked. Yeah, we are think about this node, and branch 1 we appended the left node. Okay, and it returned because the remaining become 0, so it returned. Okay, so in this case we remove left child. We finished this path. So at this point we have one remaining, so we can append the right child, or we go back to the parent node. Okay, so I think yeah, I think append right, it's almost the same. So in this case we finish exploring this path, and we also finish exploring this path, so we go back to the root node, but this node still exists as a left child, right? Does it work? Let me see. Yeah, I think so. So in this case, it doesn't consume remaining number. Just go to the parent node. Oh, but it's not good because after we go back to the parent node, we call recursively, so it go to left child again. So yeah, the infinite loop happens. So that's not good. Okay. And also I'm thinking about how to return the answer. Yeah, because this is the pointer, so we have to copy the binary tree. Okay. A binary search tree. So okay, my mistakes. Okay, binary search tree means the node have value and the left child should be less than the node and the right child should be greater than the node. I totally forget it. So how to do that? Okay, so the idea that comes first, we choose every number as a root node, and yeah, we start it. Yeah, so when it starts with 1, we have 2 and 3. So yeah, we check those two patterns and both are more than 1, so append the right node. And yeah, and it follows like this. Okay, and when we choose 2 as a root node, we have 1 and 3, so we append 1 and yeah, when we try to append 3, the 3 is more than 2, so it should be like this. Okay, so in this case we have just one pattern. Yeah, okay. Okay. So when we choose 1 as a root node, there are two possibilities, two patterns, because 2 and 3 is more than 1, more than root node. So yeah, there are patterns. Okay. I'm getting it. So okay, and n is not big, so wait. Yeah, this is similar to generation of similar to permutation 1 3 2 and 1 2 3 and 1 and 2 1 3, but 2 3 1 2 3 1, yeah, 2 3 1 would be duplicates, because when we handle 2 3 1 2 3 1, we append the 3 to this node, to this binary search tree. The 3 should be right side, but yeah, so 2 1 3 after 2 3 1, but it's gonna be same, it's gonna be the same. So yeah, we have to handle it, yeah. That's a problem. That's a problem. Yes. Mm. 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 Okay, let me generate permutations. How to do that? Permutations. How do I do that? Permutations. Choose one. Nums is 1n plus 1. And I think we call gentry function here with I, and we define gentry, and yeah, it takes value, and but we should return root node is initialized, and no. Okay, how to manage the indices, how to manage the remaining indices. Okay, so first the index is 0, and it points the head of this array, so it is 1, so we use 1, and then we have to choose next number. Okay, how to manage the indices? Let me see permutation code. But I think this is not good. The copy happens. Backtracking is used flag. Okay, let me use this idea. Used flag. Okay. Used flag is for permutations. So yeah, so there is still the problem how to remove the duplicates. 213 and 231 is the same. are the same. So 231, 231. For permutations, we use backtracking. And we use index, and if not used, so we declare the tree here because the backtracking always construct single tree. Yeah. So it's enough. We have one tree here, and call backtracking tree. We should think about 3. So in this case, 2 patterns, two on the left side, and yeah, 4, 5, 6, right? Mm? Mm. Three, one, two, four, five, six. 3, 1, 2. 3, 1, 2. 3, 1, 2. So they are same. Three, 5, 4, 6. 3, 5, 6, 4 is the same. 6, 4, 5, 6, 5, 4. They are different. Okay. But how to check this? The first case is like this, and if I choose 1 as a root node, the remaining are in right side. Two, 3. 2, 3, 4, 5, 6. Okay. I think I can, but let me think about how do I return the answers. This is another problem. So I think about this problem first. Yeah, because the node is the pointer, so it there's need to copy the whole tree. Right? Yeah, I think so. Hmm? One, two, 1, 2, 3. I just want to the confirm how it works. Yeah. Yeah, right. So, how to capture the tree this point at this point? Maybe it's very hard. So the solution is like this. One, two, and one minus. Okay. So this is basic strategy. We initialize a root node for each path. Okay, that means we have to be able to check if the combination is the same as the previous one or not. Okay. So How about generating these permutations at first, and after that we construct binary search tree for each path. Yeah? Yeah. Yeah, generating permutation. The time complexity is n factorial. n factorial. Yeah. And generating so n factorial times but the element is 8 at the most, so it's constant. It's constant or it's n. It's n. Yes, it's n. Okay, so not too bad. 8 because n is 8. Okay. And how to generate the permutations, and not permutations. Permutations with some filters like this. In this case, 3 comes first, and 1, 2, 5, 4, 6, and 3, 1, 2, 5, and then 6 comes in, but we don't count because 5, 4, 6 and 5, 6, 4 would be the same. We have to detect it. And also I realize this case 5, 4, 6, 5, 4, 6, and 1, 2. This is also same. Okay. How how do I detect this? This approach is not good. Hmm. Hmm. 3. Ah, difficult. Mm, mm, tree node. Hmm. how to implement. The tree node is defined in the system side, so we cannot change this. We cannot add the new function for tree node. So how to construct okay. So maybe this should take tree node, and if it's the current node and the index to append. So if if node value node, it should be right side. Yes, it should be right side. So node right is tree node nums edx and call this function, and really? Wait. I'm confused. I cannot even construct the binary search tree. So how to do that? To construct BST, it always look at the root node first. Okay, that's correct. Yeah. Build BST and it should always look at and node to append. Yes. Root parent rather than root. Parent value node value. Node should be right side, so we called build BST parent right and pass the node. And I'm thinking about like this root initializer root. And for build BST core with 3 nodes and append root. Yeah. This is the skeleton. But of course this is not correct. We have to generate permutations. And how to detect the duplication or while constructing the BST, can we detect it? No, that's impossible. My yeah, 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 yeah. My image is like this. Huh? But how do I get the root node? Binary search tree. 0, 1, 2, 3, 4, 5, 6. No, I gave up. I give up. Let me see the solution. Generate trees, start and end. Memo. What? Root start to end. Root value generate trees. Start root value -1. Left trees. Right trees. Left trees. Right trees. I cannot understand. Define a class solution contains a method generate trees which takes an integer n as input and return a list of optional tree node objects. Check if n is 0. If it is, return an empty list since there are no possible trees with 0 nodes. Initialize an empty directory called memo. This dictionary will be used to store previous computed results for specific ranges of values to avoid redundant calculations. Yeah, that makes sense. Define an inner function called generate trees that takes two parameters, start and end, which represents the range of value for which binary search tree needed to be generated. Inside the generate trees function, check if the tuple start and end exists as a key in the memo dictionary. If it does, return the corresponding value from the memo dictionary. Yeah, that makes sense. Initialize an empty list called trees. This list will store the generated trees for the current range. If start is greater than end, append none to the trees list, indicating an empty subtree. And return the trees list. Loop through each value root inclusive recursively call generate tree function for the subset with the start root -1 and store the result in left tree. This algorithm generates all possible unique binary search trees with n nodes by considering different ranges of root values and recursively generating left and right subtrees for each possible root value. The memo dictionary is used to store previously computed results, reducing redundant calculations and improving the efficiency of the algorithm. The memo idea is good, and this structure, yeah, makes sense to me. Yes. But okay. Maybe I can understand. So we use build build trees, yeah, and it takes start and end. Okay, so we want to, yeah, zero n minus 1 or I don't know, but okay. And the basic concept is choose the root in this range. Okay, so range start to end domains inclusive range 1 plus 1. Yes, so the trees right, and left tree, it's like recursive, and I choose the root, so the left side is it blue -1, and likewise root +1 to end. Okay. Yeah. So basically, basically start is less than end, but sometimes yeah, with even possibility end is less than start, because we loop start to end. The basic concept is, for example, 1, 2, 3, and the root is 3, so we call 1, 2, and 4, 6. So we want to choose root node from this range. Left tree is list, so we have to check we have to generate all possible combinations. right? Or yes. Mm. And we have root node, so root node is tree node. Value is root lt rt and trees append root node. In this loop, but wait. Oh, makes sense. Because we use the root here, so this range and this range don't include the root. So we don't have to think about it. And also the left trees should be less than the root, so this range is fine. Yeah, we don't think about the numbers more than root is in the left side. Okay, so we can do it like this. And we choose every number as a root. So this function returns all possible trees. And to reduce computations, we declare a memo and if memo start and return memo start end. And return tree. We should memorize. Like this. How about this? Okay. Key error. Key error. uh, default text. How about this? Storing. Hmm? Is not valid value for the expected return type list tree node. Hmm? Hmm? Where is the problem? Hmm? It's almost same. But this is not good. Generate trees. And declare trees, and start is more than end. Return the and range from start to end +1. Root -1 +1. Call recursively and loop through left tree and right trees, and we generate the tree node, root node, and append it and memo it. Okay, what is the difference? Oh, really? Okay. So, okay. Let me review. In my thought at first, I wanted to generate all of permutations and remove the valid combinations. Yeah, but this solution use the property of binary search tree, so we can divide it into two sides, left and right, and the left tree must be less than root node, the parent node. So we this is like top-down solutions. First, we choose the top and divide it into two sides, left and right, and the upper bound of the left side gonna be root -1, and the lower bound of the right side gonna be root +1. So we don't think about the duplicates because oh wait, why this work? Okay, let me see the simple one. 1 3 2 1 2 3. In this case, we choose 1 as a root, so we have two patterns because the right side have two values more than 1. Yeah, so it generates two patterns. But if I choose 2 as a root node, we should remove this case. But in this solution, we choose 2 as a root, and yeah, okay. When it is the range is determined by the root, so the order is not the problem. Okay, 1 and 3. So we don't we don't think about these two cases, or we don't think in this way. Yeah, we just think about the structure. So choose 2 at first, and after that the range is determined. The right range is determined. So we shouldn't think it in this way. Yeah, right. So yeah, that's more structural. And yeah, we determine the range, so it builds trees recursively. Okay. So we handle this case. We can handle this case because we don't care about the order. We just choose the root and divide it. Divide and conquer. Okay. Yeah, and the memo is another memo is another keys to solve these problems, because yeah, there are a lot of same sub problems. So the memo works here. Okay, let me submit it. Okay, and I'm curious about the DP, dynamic programming solutions. But it's almost the same. And this solution doesn't use the memo, right? This is the approach dynamic programming. Okay, I'm wondering this. It have helper functions. Node root left right. This is difficult. DP table where DPI will store all the unique I nodes. Initialize DP0 with a single representing empty trees. Iterate over number of nodes for every number of nodes from 1 to n. Iterate and construct all possible trees with number of nodes. Choose root for every possible root numbers within the current nodes. Iterate and use the root. So it constructs with from the small numbers dp knows append knows root minus no. Yeah, and choose root. This is the same, and use previous computed subtrees. Root minus 1 is the for the subtrees and right tree. Ah, I see. It have offset. That's so smart. Since the right subtree value will be affected by the choice of the root, clone the right subtree with an offset equal to the root value. The clone function handles this. Yeah. Okay. Okay. This was so difficult. I'm not familiar with binary search trees, but I learned. Okay, let's go next problems. Given an integer n, return the number of structurally unique BST, which has exactly n nodes of unique values from 1 to n. Why this comes first? So this is easier than previous one. Just return the number of combinations. Oh, I mistook, but it's okay. Okay. Num trees. Okay, but n is 19 at the most, so but the way of thinking doesn't change. Okay. Yes. Def. recursively, and it should have range start end. Okay, and and +1, we choose root. Okay, and number of left trees is calculated as start root -1 because yeah, this is binary search tree. Okay. So we get numbers. So the all of total numbers gonna be, yeah, total is 1, and return total. Let's use memo. Return recursive function 1 to n. Yeah. And oh, how about this case? Return 0. It's invalid range. If it is same, we loop once. So the total gonna be but times numbers left numbers. Yeah. We should check the number more than 0, because if it's there, the total gonna be 0. It's not good. Yes. Start and if it's same, we just choose the root and this returns 0 and also this returns 0, so the total gonna be 1. That's correct. Okay. Wrong answer. Put this. Wow. Like this, because we choose every root, we choose a root, so we can construct the tree with the root node. Okay, so we have count 1 and this is the number of left trees. And yeah, also we have right trees, so we multiply them. That's a number of trees when we choose this root node, but the total is total is total, so we can add the count of the number of trees when we choose one root node. Okay. Good. Okay, let's see for any given range how many permutations do we have. So let's find a solid approach before we start. Okay, so we start with left, right, 1, 2, n, and we want to return how many unique BSTs we have well, we can iterate through 1 to n and choose each value as our first root. Then we see how many structurally unique the left one has and how many the right one has. We multiply these by each other to get all combinations and add to an answer. Repeat for all elements, then return. Yes. Correct. Yeah, that's the same. Okay, let's learn English. Yeah, we use recur. We use the recursive function since we should solve the sub problem. Yeah, the sub problem here is how many trees? How many trees is there? How many trees is there? Between so this function takes start and end inclusive range, yeah, and to reduce computations we use memorization. If end is less than start, it's invalid range, so we return 0. We count the total number of trees with this range. We choose the root node. We iterate through. We iterate through the range and choose root node. The count is 1 at first, and the BTS. Should have the node whose value is root minus 1 at the most. The left side range is like this. Yeah. We define the sub-problem and the function to solve it. We just call the function recursively. When the number of left trees is 0, it's invalid and affect the count. So we avoid multiplying memo it. Please review English. We will use recursion because the problem naturally breaks into subproblems. The subproblem is how many trees can we build with values in the range start to end. So this function takes start and end as an inclusive range. Okay. To avoid recomputation, we use memoization. Okay. Oh, really? We will count the total number of unique BSTs we can build for this range. We try every value in the range as a root node. We start with count equal 1 for the current node, then multiply by the number of possibilities of the left and right. The left shrub tree must use values less than the root, so its range is Is this technically wrong? Return 1? Really? Oh. Exactly. Oh. Oh, it doesn't affect. Okay, okay. Okay. Interleaving string. Okay. Let's go. Given strings S1, S2, and S3, find whether S3 is formed by an interleaving of S1 and S2. An interleaving of two strings S and T is a configuration where S and T are divided into N and M substrings respectively, such that N minus M stamp 1 interleaving means. Huh? No. N and M substrings respectively. So in this case, two substrings. So two substrings here. And N minus N, the difference between N minus N should be within 1. Okay. One way to obtain S3 is split S1 into S. Deriving the two splits, we get pum 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 pum. So 3 substrings and 2 substrings. 1, 2, 3 and 1, 2. It feel like difficult. The length of S1 and S2 is 100 at most. Okay. Interleaving. N and M. Divide it into N and M. So yeah, the N is gonna be length of S1 at the most. Okay. Yeah. I'm at a loss. Okay, maybe this is we will use dynamic programming. Because it cannot be solved by greedy. We should check the combinations. How to the answer is Boolean. Okay, so think about this case, and yeah, I'm thinking about from the end. So in this case, like this, but it's not accurate. Just an image, my image. So we calculate and memorize the result of the previous we should store the previous result. We can do it or not do it. But there are a lot of paths to reach the final strings, because for example, in this case, this case we lose three characters CAC. In this case, we how is the remaining characters CAC? Cannot find the CAC. Yeah. Okay. How about this? CA. No. We should find the AC, but there is no AC. In this case, we should find the C. Okay. We can find the C in the S1, so we use the S1. Or we are going from the start. Example, the first character is A, so we should use S1. DP A and we consume the first A from S1 and S2 doesn't change, we go next dp AA if we use the previous result, we should find the A. Okay. So like this, but the result is that end with the same result. If I start from the empty, we should find AA. So yeah, we can find the AA from the S1 like this. And another case, if we start with the previous result, we already constructed A, and the remaining strings is like this. We look at these strings and we should find the 1A, so we consume the A from the first strings, so the result to be like this. That's the same. Okay, how about this case? Yeah, so A, B, C, C and B, B, C, A. Right, so we have two patterns. So yeah, there are a lot of possibilities. For example, how about this case? うんうんうんうんうんうん。So maybe they are need to go through this string start to the end. Yeah, and when we reach the end we can find, yeah, we can achieve it. So how about use the index? In this case 0 1 2 3 4 5 6 7 8 9. No, 0 is here, so 0 means 0 and 9, so it's 10. 2. So the space complexity is like 100, 100, 200. Not bad. Okay. But how to implement the transition? Think about this case AA, and there are two patterns, so it use 1 and 1, also true, and 2 and 0, also true. The ideal transition is, for example, if we have calculated the AA, the remaining strings is like this. So we we look at start from start. We look at the string from start, db, dbbcb, and how to we should find a D. We should find the D from the string, from these strings, and find the D. So we should look at the index 0. So in this case, we find the D from the string 2. So we loop through the string 1, loop through the index of string 1, and when the index of string 1 is 2, we can find the index 0 and the value is true. Okay, so we can use the D and update the AAD. We can update the AAD to 1 and 2. Okay, and the next character. Let's go to the next character. AADB. So we should find the B from these strings, and we find the B from the string 1 and from string 2, and second two B's in the string 2. So we have 3 patterns. We have 3 patterns. So we go zero, 1, 2. We find B. So it requires the index should be 2. Index should be 2, and the other index doesn't matter. Okay, other index doesn't matter. The other index doesn't matter. So we just look at the index 2. But wait, how about this case? AA, DPAA. We just we should look at only AAD because we are looking at one by one. Okay, so first of all, we look at this, and then the index is 2. Yeah, index 2 is here, so we can use it. 3, 1, 2. And is there other case? We look at AAD and we can find the B index 1, so we look at here, and yes, it is true, so we true, we can update it. And how are this? The index 2 of string 2, so we should find in AAD, and this doesn't matter, and this should be 2. Okay, but 2 is false, so we cannot use it, so we update like this. Okay, and yeah, Okay, looking at characters one by one is a good strategy, because if we can make this string, it means we can make this string. So we look at one by one, and the final validation is whether we can consume all of the strings. Okay, that is a condition to solve these problems. Okay, if they are all used, it means we could divide these strings into n and m substrings. So it means we solve the problem. But if it's not end of the index, it means that's not interleaving. But the end of character doesn't specified. end of character isn't specified here, so for example, if there is additional characters, it means divide 3, and this is also divided into 3 substrings, but yeah, we just use first 2 substrings. Is this violation? I'm not sure, but let me try this idea. S1, S2, and S3, and we should declare DP, that is 3D arrays. Yes, DP first of that's a dictionary. So we use default dict of list. Okay, and for I in range C, and if I is 0, that's a base case, so we will handle the base case here 0. That means the DP we use slice expressions, and the DP be initialized like this, and if it's since it's single characters, so we just check the first character of both of string 1 and 2. Okay, and so the target, we call it target, and Okay. We should initialize the we should initialize the default dict target dp target false the column and row b. Oh, I see. Previously, when I thought we should iterate over the string, but I realized we have the current. We check one by one, so we have current and a new character, so the transition is more simple. AAB. Yeah, okay, I find it. The sum of them should be same as I plus 1. So JK I plus 1, so 0 to I plus 1 means m plus 1. Okay, and k might 0, but m minus j plus 1. So if m is 1, the j is 0, 1, so 0, 1, 0, 1. And m is 2, j is 0, 1, so don't need to plus 1. M is 1, so m is 1. J 0 or 1. J is 0 or 1. M is 1. If J is 0, zero, 1. I see. Don't need to loop. M minus J. 1 minus 0. 1 minus 1. Okay. True or false? True or false? Two patterns. K minus 1, so it means this time we use K, so the K S2K must be the S3M. No, M minus 1. That means I. Hmm. Check the value. Check the index. Yes, and finally, follow. Low. Like this. I'm not confident. Out of range. Okay, -1. Not sure. J K target and print. True. false, 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 false. Too many false. All false. Let's take a break. I will finish this stream for now, and I will come back.